Alright, so today we're going to start our unit on acids and bases, and we have a definition of acids and bases that you're going to be using for this unit, which is the Bronsted-Lowry definition. So we're going to be talking about conjugate acid-base pairs, meaning a pair of compounds, one is going to be a reactant, and the other one is going to be a product. And they differ by the presence of H+. So the conjugate acid-base pair, the reactant might have more hydrogen or less hydrogen than the product, but the fact that the hydrogen has been transferred in the reaction makes it an acid-base pair. So an acid is one that donates the proton, the H+, in water. And if we have an acidic solution, then it has the hydronium ion present, which is H3O+. Basically, it is H+ attached to H2O, signifying the solution is acidic. So if you see H3O+, that's the same thing as an H+ plus H2O. A base accepts H+ in water, and therefore we have the hydroxide ion, which is negatively charged. It's when an H+ is missing from H2O, and it signifies the solution is basic. You may have heard of pH or POH, which talks about the concentration of hydrogen proton ions or the concentration of hydroxide ions, and we'll get to that later in this section. All right, so figuring out acid-base pairs, what you need to remember is that the acid donates H+ and the base accepts H+. So in our reactants, one of them is going to be the acid and one of them is going to be the base. And then on the other side, you have the conjugate acid or base. So here we have HNO3 and H2O. So you have to compare the reactant compound to what it's going to look like in the product to figure out if it donated hydrogen ion or if it accepted the proton. So HNO3 changes into NO3 in this reaction. So it has one less H, meaning that it's the donator. So this is our acid, and then on the other side it is our conjugate base. It differs by one proton. H2O in this example is going to become H3O+, so therefore it has one more proton, meaning it's the acceptor, so that is our base. And then on the other side, the compound is our conjugate acid. So they get paired up, conjugate acid-base pairs. Notice that our arrow is going back and forth like an equilibrium, meaning that if the reaction went in the opposite direction, it shifted left. Our NO3 is now the base because it's accepting hydrogen to become HNO3, and H3O+ is our acid because it is giving up hydrogen to become H2O again. All right, NH4+ and H2O. You have to look at the product to see how it's changed. NH4+ to become NH3, well, it has given up a proton, so it is an acid. So this becomes our conjugate base. H2O becomes H3O+. It has gained a proton, so that is our base, and the other one is our conjugate acid. Again, they get paired up, acid-base pairs. All right. More H2PO4 plus H2O. Again, you take a look, hey, over here, it's only HPO4, so it's missing one hydrogen. That means that this was the donor, our acid. This is our conjugate base, and water, again, acts as base, and H3O+ is our conjugate acid. Okay, well, water can act as a base, as we've seen in the last few reactions, or it can act as the acid. So here we have H2O plus NH3. Well, let's take a look. In the resulting product, we have OH minus and NH4+. So ammonia becomes ammonium. It gains a hydrogen, so that must mean it's the base, it's the acceptor. And water this time is acting as an acid. And it leaves us with OH OH, the conjugate base. Remember, the presence of hydroxide means that it's basic, and the presence of our hydronium ion means that it's acidic. Okay, H2O plus is going to act as the acid again and donate its proton to PO4, 3 minus, and here we have our pairs. All right, so go and practice that. The last thing that you need to know is the strength of the acid or the base. The stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. You need to know these strong acids. You have to memorize them. Sorry. And then the strong bases are mostly hydroxides or oxides with group 1 metals. When we write the reactions, you need to make sure that you know if you're dealing with a strong or weak acid or base. It also depends on how we're going to do our calculations later for pH and POH. But strong acids and base completely dissociate, so one arrow, one direction. Weak acids, weak bases partially dissociate. We have equilibrium. Hey, we're going to be writing equilibrium expressions. Ka is going to be the same thing, concentration of product. Over reactants, we're going to continue with our equilibrium with our weak acids and bases. All right, so hydrochloric acid, it is on our list for strong. So when it dissociates completely. You only need an arrow going in one direction. It splits up into H plus and fluorine ions. All right, sulfuric acid, also strong. So because it donates one proton, we're left with HSO4. All right, and then beryllium hydroxide is a strong base. So when it dissociates completely. Beryllium has a charge of 2. Okay, and beryllium 2 plus 2OH minus. And the last one, ammonia, is a weak base. So when we write weak bases, we must include water in our reaction because water has to be the donator of that proton because it is a weak base. So we write our ammonia plus water. Water is going to be acting as our acid. Notice our equilibrium arrows going in both directions. And we get ammonium plus OH minus. And the presence of this OH minus tells you it's basic. Presence of H plus or H3O plus is acidic. All right, that's it. Bye.